students, today we will discuss another important concept in organic chemistry. First of all, why do organic compounds participate in reactions? It is due to electronic effects. So here electronic effects means shifting of sigma electron pairs or pi electron pairs or lone pairs of electrons in molecules. Here these electronic effects are classified into again various types like inductive effect, mesomeric effect, or which is also known as resonance effect, hyperconjugation, electromeric effect. We will see these in detail. After that, we will find many applications of these electronic effects. Based on these electronic effects only, one can understand acidic strength, basic strength, reactivity order, all these in organic reactions. So first we will see inductive effect. You know what is a covalent bond? Again polar covalent bond, non-polar covalent bond. If there is electronegativity difference between two bonded atoms, and if bond is formed by sharing of electron pair, then the bond is called polar covalent bond. In polar covalent bond, electron pair is attracted towards more electronegative atom. For example, let a carbon compound in which chlorine is present here. Chlorine is more electronegative than carbon, then this electron pair is attracted towards chlorine, then this chlorine gets partial negative charge. Now the electron pair is moving away from this carbon, then this carbon gets partial positive charge. Then this carbon is electron deficient, it attracts electron pair from adjacent carbon, then this carbon also gets partial positive charge but smaller than that of this one. Like this effect is continued till the end of the chain, but the effect will be decreasing as the distance between this electron withdrawing group, attracting group and electron giving group increases. Now we will see what is this inductive effect. Here there is a polarization of sigma electron pair towards electronegative atom. This is called inductive effect. That is polarization of sigma electron pair towards electronegative atom of molecule is called inductive effect. Then in this there are some groups which attract electrons or withdraw electrons, some groups which donate electrons. The groups which attract or withdraw electrons are called minus inductive groups or minus I groups. Now we will see what are these minus I groups. Strongest minus I group is NF3 plus, next NR3 plus, NH3 plus, after that NO2, CN, after that CHO, keto group, carboxylic acid group, then halogens, fluorine, chlorine, bromine, iodine, after that OH, NH2. These are some minus I groups. They withdraw, that is attract electrons from sigma bond. Then some groups they release electrons or donate electrons, which are known as plus inductive groups. These are O minus, COO minus, then tertiary butyl group. This is tertiary butyl. Isopropyl group, ethyl group and methyl group. Or you can say this is tertiary alkyl greater than secondary alkyl greater than primary alkyl. So these are plus I groups. If we take isotopes of hydrogen, after this deuterium and hydrogen. Deuterium also shows plus I effect. The plus I effect of deuterium is greater than that of hydrogen, protium. This is inductive effect. Then another one is mesomeric effect. Delocalization of pi electron pairs through a conjugated mechanism is called mesomeric effect. Here delocalization of pi electron pairs is also known as resonance. Delocalization of pi electron pairs. Okay, here again this delocalization is observed when either two pi bonds are in conjugation, or a pi bond and a lone pair is in conjugation, a pi bond and a positive charge is in conjugation, a pi bond and a negative charge is in conjugation. Now we will see what is this pi-pi conjugation. Conjugation means if two pi bonds are separated by a single bond, or conjugation means if two groups are separated by single bond, then it is called conjugation, like this. So here CH2 double bond CH double bond CH2. This is a buta 1,3-diene. Now if we take this one, here a pi bond, this is a pi bond, and these two are separated by sigma bond. That's why this is called pi-pi conjugation. Similarly, if there is a lone pair separated by single bond and that is conjugation with a pi bond. For example, if we take this vinyl chloride, so in this vinyl chloride, chlorine has a lone pair, here is a pi bond, this is lone pair. Now these two are separated by sigma bond, that's why this is called pi lone pair conjugation. Then if we take another one, that is pi positive conjugation, CH2 double bond CH2 plus. This is called allyl carbocation. Now observe this one. This is a pi bond. This is a positive charge separated by sigma bond. So this is called pi positive conjugation. Then next one is a pi negative conjugation. Let here a negative charge. Same thing, pi bond, this is sigma bond, this is negative charge. So pi bond and negative charge are separated by a sigma bond, then it is called pi negative conjugation. Now we will take in this mesomeric effect groups which show plus mesomeric effect, minus mesomeric effect. Plus mesomeric effect means they release electrons towards pi bond system. Minus mesomeric groups means they withdraw electrons from pi bond system. So if we take first of all plus mesomeric groups, they release electrons towards pi conjugation. So to show this plus mesomeric group, the atom which is attached to this carbon with a pi bond should contain either negative charge, that is excess of electrons, or lone pair of electrons. So if we take this one, oxide ion. See, same oxide ion shows minus I effect, but when it is in conjugation with the pi bond, it shows plus M effect. Then NH2, here there is a lone pair on nitrogen. When it is in conjugation with the pi bond, then it shows plus M effect. Similarly, a primary amine, this is a secondary amine, and a tertiary amine here NR2. Then after this we have OH, OR. Even this halogens show plus mesomeric effect, and plus mesomeric effect of halogens is fluorine, chlorine, bromine, iodine, because they contain lone pairs of electrons. Because of this lone pairs of electrons, they show plus mesomeric effect. That is, now minus mesomeric groups, these withdraw electrons from pi conjugated system. If we take this minus mesomeric NO2, Cn, SO2R, this is a sulfonide group, sulfonic acid group, SO3H. After this CHO, C double bond O, COOH, COCl, CONH2, etc. These are some minus M groups. Now coming to the next one, that is hyperconjugation. So this delocalization of a sigma electron pair from CH bond, sigma electron pair, towards an unsaturated system is known as hyperconjugation. So in this hyperconjugation, there will be overlapping of filled sp3 hybrid orbital of alpha carbon with empty p orbital or empty pi orbital. Now we will see how to find out this hyperconjugative structures. For example, I will take ethyl carbocation. This is ethyl carbocation. Now this is unsaturated system. It contains empty p orbital. Now the carbon attached to this carbon which has empty orbital is called alpha carbon. Now the electron pair from this CH sigma bond will be delocalized towards this unsaturated system. Then here this hydrogen is shown without bond, so it becomes C, H, H, and here H plus double bond CH2. And in next step or in next hyperconjugative structure, this electron pair involves in hyperconjugation. So it becomes H plus. Here this hydrogen is shown without bond. That's why this hyperconjugation is also known as no bond resonance. In resonating structures, hydrogen is shown without any bond. That's why it is called no bond resonance. Now next structure, this hydrogen is shown without any bond. This one. Now if you see here 3 alpha hydrogens, 3 hyperconjugative structures plus 1 basic structure. This is called basic structure. The number of hyperconjugative structures are 3. The total number of structures is 4. Basic structure from and 3 hyperconjugative structures like this. Similarly, if we take a carbocation, sorry, this is carbocation, then if we take a free radical, we will take this free radical which is known as a isopropyl free radical. Now, this is unsaturated carbon because it is deficient in electrons to get octet. That is why it is unsaturated. So, next carbon is alpha, similarly this carbon is also alpha. Then total how many alpha hydrogens here? 6 alpha hydrogens. We can write 6 hyperconjugative structures. I will write just one structure, remaining you can see in the same way. Now, this electron requires one more electron to form a bond. So, it is shifted in this direction. Now, one electron from this is taken to form a bond and another electron left at this hydrogen. So, its hyperconjugative structure is written as HCH. This hydrogen is shown with a single electron. Now, a double bond is formed here, CH3. So, next you can show this with a single electron, next similarly these 3 also. So, total how many hyperconjugative structures? Number of hyperconjugative structures is equals to how many? 6. Number of hyperconjugative structures equals to number of alpha hydrogens. So, that is 6. Now, another one is a temporary effect, that is electromeric effect. Whatever the effects so far we discussed are permanent effects. Permanent effects means even in absence of reacting reagents, these effects will be operating. That is why they are called permanent effects. If electronic effect is operating in presence of a reagent, then it is called temporary effect. So, fourth one what we have is electromeric effect. This electromeric effect is temporary effect. This is a temporary effect. This one. Okay, we will see one example. Let this is an alkene. H plus is reacting with this one. H plus is electron deficient. That is why this pi electron pair is taken by this hydrogen. So, this effect is called plus electromeric effect. If electron pair is shifted towards attacking agent, then it is called plus electromeric effect. So, here this hydrogen forms a bond by taking electron pair, then the other carbon becomes positively charged. This effect is called plus E effect. If electron pair is moving away from the attacking agent, then it is called minus E effect. For example, if we take a carbonyl compound, that is a ketone or a aldehyde, in reaction with a nucleophile, say cyanide ion. Cyanide is rich in electrons, negatively charged. So, when it is attacking at this carbon, this pi electron pair is shifted away from carbon. That is why this effect is called minus electromeric effect. Then here it is like this. This is a temporary effect because it is operating only in presence of these attacking agents. Now, come to important application of these electronic effects, that is okay. First we will see stability of carbocations. A carbocation means a species in which one of the carbon atom has a positive charge, that is carbocation. So if we take alkyl carbocations, the stability of alkyl carbocations is explained on basis of plus I effect and also hyperconjugation. Stability related to plus I and plus H, hyperconjugation. Okay, here more than plus I or more hyperconjugation, more is stability. Now we will take different alkyl carbocations. We will take tertiary butyl CH3. This is tertiary butyl carbocation. Now see, this is unsaturated carbon. Then how many alpha hydrogens here? Total 9 alpha hydrogens. So 9 hyperconjugative structures. Now I will take a secondary carbocation, that is isopropyl carbocation. Now this is unsaturated carbon, alpha carbon, alpha carbon. So total 6 alpha hydrogens means 6 hyperconjugative structures. Here 9 hyperconjugative structures, here 6 hyperconjugative structures. Then we will take ethyl carbocation. Then how many alpha hydrogens? 3 alpha hydrogens means 3 hyperconjugative structures. Suppose if you are asked total number of resonating structures, you have to include one basic structure. So 3 plus 1, 4 resonating structure. If you are asked only number of hyperconjugative structures, for this only 3. Similarly, for this total number of structures 10, for this one 7, like that. Then methyl carbocation. Methyl carbocation. There is no alpha hydrogen for this. So there is no hyperconjugation. No hyperconjugation. That is okay. Now more the number of hyperconjugative structures, more is the stability. So what is the stability order? This is the stability order. Now come to aryl carbocations, like benzyl carbocations. CH2 plus. This is a primary benzyl carbocation. The stability of benzyl carbocations is based on resonance. So if you write resonating structures of this one, this pi bond is shifted in this direction, that is delocalization, resonance. Why there is delocalization? Since this pi bond and positive charge are in conjugation, that is why delocalization takes place. Then we can write resonating structures like this, double bond here, CH2. Then in next structure, this pi bond is shifted in this direction. Next structure, And finally, these are resonating structures. So, more the number of resonating structures, more resonating structures, more is stability. So, if we take C6H5, this is also written as C6H5CH2 plus C6H5 CH, or we will take tertiary C6H5 C6H5 plus C6H5 CH C6H5 plus C6H5 CH2 plus. This is a tertiary benzyl, secondary benzyl, primary benzyl. So, here one ring, these electrons involved in resonance. Similarly, here 3 rings, the pi electrons from all the 3 rings involved in resonance. That is, this one has more number of resonating structures, so it is more stable than the secondary and primary. More resonance, this one. Now, coming to general stability order of this. A tertiary benzyl carbocation is more stable than that of secondary benzyl carbocation is more stable than that of. Here this is a very important one. There will be confusion in this one. Tertiary butyl is more stable than that of primary benzyl. In some books it is given in reverse, but based on heat of hydrogenation values, this is found to be more stable than this one. Here it is not based on either resonance or hyperconjugation. This is based on heat of hydrogenation value. So, tertiary is more stable than that of primary benzyl, than that of this is allyl carbocation, then isopropyl, then ethyl, then methyl, then phenyl C6H5 plus, then vinyl CH2 double bond CH plus. These are least stable carbocations. This is a stability order, and this is called allyl. This one, allyl carbocation. This is also stabilized by resonance. That is. Now, coming to next one, stability of free radicals. Or in this we will see some more in depth. Electron donating groups increase stability of carbocations, and electron withdrawing groups decrease stability of carbocations. That is, for example, if you take here CH2 like this one carbocation, CH3 CH2 CH2 plus. What is the nature of this NO2? This is minus I group. Minus I group means it is electron withdrawing. Already this carbon is electron deficient. Still this NO2 group is trying to pull out electrons from this electron deficient carbon. That is why this becomes less stable. So, this is the stability order. So, if there is a minus I group, stability decreases. We will take some benzyl carbocations, CH2, Here let OCH3. Here NO2. Now if you see this one, this is a minus I group and also minus M group. It is strongly electron withdrawing group. Whereas this one is a plus mesomeric group. Minus I and plus mesomeric, but plus mesomeric is considered here. Then it is giving electrons to the system. Whereas here no group. Then if you take stability order of these three, which one is most stable? 2 is more stable than 1 than 3. This is stability order. Okay students, tomorrow we will discuss some more important applications of this electronic effects.